Lecture, we will talk about uh, propagators in quantum mechanics. We'll talk about propagators in quantum mechanics. Well, we are going to talk this not only in the Schrodinger picture, but also we will do it in the Heisenberg picture. So first, we will talk about this in the Schrodinger picture. Well, to give a quick review, let me start with the following thing. So consider you have a function f of t, and this function satisfies a differential equation that looks like d f of t divided by dt is equal to some constant k into the function f of t itself. Now let's try to solve it and see what do we gain from here. So we get df divided by f, remember f is a function of t, is equals to k dt, and then integrate both sides as usual. So how do we integrate? So we have to set the limit, and this is how we set the limit. So for t equals to t initial, the value of f, let it be f of t initial, and when time is t final, let the value of f, which is the final value of f, is t final. So this is the integration limit for f, and then it's very simple. You get ln f, and you get f of ti, and limit f of tf equals k tf minus ti. Now I can skip some steps since it is very easy to do, and I'm writing the final result. The final result turns out that f of tf, that is value of f when we have final time, is equals to exponential e to the power k tf minus ti multiplied with f of ti. So what is this equation and what it is trying to say? Well, what you have at hand is a function f, and you have two values of the function, one at t final and one at t initial. And this equation 1, it tells you that if you know the function at t initial, then using this equation you can find what the function is at t final. That means if you look at the structure of equation 1, all you can do is you can talk about how the function evolves in time, but you cannot say anything about how the function evolves in space or with respect to position. So similarly, if you look at Schrodinger equation, so yeah, so similarly, if you look at the Schrodinger equation, it's almost the same as above, but with little bit change. We have I h cross here, and there is a d psi, which is a function of t divided by t dt, and instead of constant k you have h, which is the Hamiltonian, and again you have psi of t. These psi of t are actually in ket. That means these are the states of a quantum system. Now we all know the solution of this. I don't have to do it, you can do it. And it turns out that you can write the state psi of tf, which is the state at final time, is equal to e to the power minus I by h cross. So you have to do the same way, the way we did the last equation. So everything is almost same with little bit changes. So this is the exponential term, and here we have psi of ti. Or more precisely, in a very short manner, I can say that the value of the state at final time tf can be calculated by using this time evolution operator tf comma ti, and a u there is equal to this exponential term here. So the exponential term in short is represented like this, and this is the initial state. So as you can see that this equation is trying to tell you that if you know the state of a quantum system or a quantum particle in the initial time, then you can always use this equation 2, and using this time evolution operator you can always say what is the state of the quantum system in the final time or after certain time, tf minus ti. That's the time interval when the wave function evolves. Well, I have not I'm talking about states, and this is how the states evolve more precisely. And you can see the interesting thing that we only have the evolution with respect to time. It says how the state of a quantum particle evolves in time. So, for example, if I say that there was a quantum particle and the wave function of the quantum particle at initial time can be given in this way. We all know how to represent the states in the position representation. So this is my wave function of the quantum particle in the initial time. Then I can also write like this, which is psi of Tf, which is position representation of wave function of the quantum particle at time Tf. And what do you have now? What you have at hand is now that from the above equation, you can infer that if you know what is the wave function of a quantum particle at time ti, you can say what is the wave function of the quantum particle at time tf. But now carefully look at these positions q here and q here. So that means you are looking at the wave function of a particle at time ti and at space at coordinate x, but we know that the wave function spreads around that coordinate, so not precisely that coordinate, but however, the point is that the wave function only evolves in time, and this is what this information is there, what is in the Schrodinger equation. But I want to consider a situation, a different situation. So I want to check out, is it possible that I have a quantum particle whose wave function at some position qi and some position ti is known, and then the quantum particles not only evolves in time, but it so happens that it starts moving in space. So the whole idea is there a way I can go from psi of qi ti to psi of qf tf? This is a clear indication that if you had a wave function in initial time, so this was the wave function in the initial time, so let me write it as psi I, then I want to see what happens to the wave function in the final time, but not only in the final time, but now the wave function is at a different coordinate position, that is qf. So what is the object that can relate these two? Because Schrodinger equation relates time evolution. Okay, how the time evolution of the states happen, and that also using this time evolution operator. But now we have this evolution of time, and as you can see, the space coordinates has also changed. So what will be the most normal guess for such kind of ideas? You want to go from here to here. Well, the most non-trivial and maybe simple guess for any new guy who's doing quantum mechanics is he'll say that my expectation is this. Maybe this you will have this thing here, wave function qi, and just like there was u, which was a function of only time, now I'll have some other function instead of u, maybe g, And this time these are not only function of time, but they will be also function of coordinates. So qi, ti, and this will give me psi of qf, tf. So this is the most naive guess that one can make. Okay, that's it. But it turns out this guess is almost true, apart from certain other things that will be added to the argument. Now we have our guess, and now we'll use the mathematical tools that we have, and let's try to figure out what is the actual answer to this question. So the whole idea is you have this wave function psi of qf tf. Remember, we are working in Schrodinger picture. Okay, and in the next part of the lecture, we'll do the whole analysis in Heisenberg picture. I'll let you know about this in the next lecture, but let's focus on this. So this is what we have, and we all know that this can be written in the following way. So you can write qf here and the ket state here. Okay, now comes a very interesting catch, but after one step. One more step I can add, so I can write it as qf, and remember what is psi of tf. So it is u tf comma ti multiplied with the state psi of ti. So this is what you need to remember. We just applied the thing that we obtained from Schrodinger equation, because you see this is the state at a final time, and I just represented it in terms of a state with the initial time with the help of time evolution operator. Okay. Now in quantum mechanics we have a very beautiful tool, and the tool says that if you do this, if you do the integration, and the integration is with respect to some coordinates, so let me take it as dqi, and you have such kind of base gets qi, qi. So remember, these are base gets. Then you have this identity matrix here. So this is a very interesting relation that we are going to use, and we'll see what is the physical meaning of introducing such kind of thing in this expression here. So let's do it. So what do we have at hand? So we have qf here. Okay, keep the time evolution operator here, and then introduce qi and qi. Psi of ti stays here as it is, but remember there is an integration over qi. Now this is quite interesting, and why it is interesting we'll see in a couple of times. So
Sir, here in your this last equation, okay. So you introduce u in bracket u of tf minus t initial.
tf comma ti, which contains the exponential to the power tf minus ti. Yes.
Yeah, but here you introduce tf minus ti, right? In your
No, this is
last step.
tf comma ti. Comma.
No. In that last equation.
It's in the oh here.
Yeah.
Oh, sorry. I should write tf comma ti.
Yeah.
Okay.
Okay. Fine.
It's not minus. Okay. So okay, great. So now, so that we have introduced, and let's check out what do we have at hand. So we have what we wanted. So here I have psi, which is a function of qi ti, and there is some function. So you see a function here, and this is what is my g, which is a function of qf, tf, qi, ti, and I'm going to write what this is, but you can see all the qf, tf, qi, ti are present. So I'm writing it in terms of g. But this was the naive guess that we made, But it turns out in reality there is an integration over dqi. Now what does it mean? Why we have this extra integration over dqi? And before going into that, let me shortly tell you what is this expression qf u tf comma ti and qi. So this expression is right here qf, and this turns out to be e to the power minus I by h cross tf minus ti and qi. That's it. So this is what I'm calling my g. So g has a name, and it is called as a green function, but we will check out what this is in next couple of lectures. But this is what it is. So it's a 2-point function. So you have these 2 points qi and qf and so on. Okay, so what does it mean that to get the final state of your quantum particle qf-tf, you have to write such kind of g qf-tf qi-ti. However, there is an integration with respect to qi. So what does it mean? Let's try to understand. Okay, so what happened is we had our particle at some time ti. So this was my particle at some position qi. So let me represent in this coordinate. So consider this side, this axis I have t, and this axis I have q. So any point here has a t here. So consider this is q ti, and a position here qi. So here was my particle, or you can say here there was a wave function described in this point, and so on. What happens is the wave function travels and it reaches to some coordinate qf in time tf. So this is what happens. So you started with this wave function and you ended with this wave function. And now the way you go from the initial wave function to the final wave function is through a green function, which is inside an integration. Now this integration over qi tells you that there is sum of contributions of various amplitudes. For example, so when you have integration over qi, it means not only the amplitude from qi is being summed, but there can be another value of qi, which is qi prime, because what is integration? Integration is nothing but summation, right? The whole thing can also be written in terms of summation, and in the summations you will have different values of qi's, and the contribution goes from here to here also. You can have qi triple prime, and it also adds into the sum, and it goes like this. That means you have sum of contribution of various amplitudes. So these are the various amplitudes qi ti, and then qi prime ti. But look at this interesting thing. All these various amplitudes are in the same instant of time, that is ti. What are the other various amplitudes? Q double prime ti. So, all these amplitudes, they add. Yeah. Yes.
In this figure, you said that at the initial position you can have the three different amplitudes, but in in our practical situations,
No. I said that you started with a quantum particle which has this as a wave function, right? The wave function was localized somewhere near the point qi. Okay, and this is what you started, and you ended with a wave function which is some other position at some other time. But since we are in quantum domain and we know something weird is going to happen, and the weird thing that happens is when you go from here to here, the actual mathematics is that you have to take the sum of contributions as if you are going from various initial positions at time ti to one final position qf at time tf. It is like we know what happens in light. So if you have this front of light, you want to calculate what is the say effect of this wave front or intensity at this point, then we take the sum over contribution from all these points, right? This is what we do in the light case. So similarly, in quantum mechanics, we have this kind of weird thing, which looks weird in terms of classical mechanics, because in classical mechanics we have
sir,
one point and we have another
yeah,
point. Yeah.
but sir, according to this picture that you have drawn here, so this curve like structure is our source, right?
It's not the source.
The source
Actually, it is
means,
a
yeah,
wave function. That means
it gives the
the
wave
particle is
functions
there.
for that source, right?
For the
Yeah,
say a quantum particle. Let's deal with the
yes,
quantum particle.
yes. But we say that quantum particles, we have to first of all localize it within some regions. I mean, if we have some initial
Yes, yes.
uh, coordinates, and for initial coordinates and initial time, we have to first of all localize it. After then only it
Mm-hmm.
will evolve with time,
Yes.
right?
Mm-hmm.
So,
Mm-hmm.
but in this picture above, you said that, well, you can have the different positions for that same quantum particles, or these
No, no, no.
amplitudes are for the
It's not the same quantum
different
particle.
particles.
The quantum particle is localized somewhere near qi at time ti. Okay, but when you calculate the amplitude at qf tf, you know what is amplitude? Square of amplitude gives probability. So let's try to understand this in terms of probability. So you have this is the quantum particle, and let this quantum particle is at some position qi at time ti. So when I say the wave function of the quantum particle in the initial time is this, then we know that the square of this tells me what is the probability to find the quantum particle at time ti and position qi, right? This is clear. Next is, when I said that we are trying to find what is the amplitude of quantum particle at point qf and time tf. So it not only evolved in time but also evolved in space. So it actually moved in space and time, just like a classical particle moved from one point to another in space and time, right? So then when we are evaluating qf tf, that means we should take square. That means we are going to get what is the probability of finding the quantum particle at position qf and at time tf. It turns out that when you have this information of probability, that what is the probability of finding the quantum particle somewhere localized somewhere near qi at time ti, and you want to calculate the probability of final state of the quantum particle, it turns out when you want to do this, when you want to go from psi qi ti to psi qf tf, that is, you are indirectly going from one known probability to another unknown probability that you want to know, and there is a process you can know, and the process is using the Green function that I defined, but unfortunately there was an integration over the initial position qi. That means as if we are adding the sum of contributions of all the possible wave function that we can write for that quantum particle at the same time ti, but different positions, and all of them are going to contribute to the final probability. That's the weird thing. We know the wave function for the initial quantum particle was localized somewhere near qi at time ti, and we want to find the wave function of the quantum particle at qf and time tf. But in the process of finding this, going from one probability to another probability, that is going from one wave function to another wave function, the whole process includes the idea of summations, and the summations of various amplitudes. By various amplitudes, so if I write an amplitude, what are the various amplitudes? So apart from Qi Ti, I have one more amplitude, Qi prime Ti. What does it mean? It means that this is as if there is the same quantum particle can be at, I'm not saying the same quantum particle is at different places at the same time. I'm not saying that. I'm saying that consider the scenario when you want to go from this to this. Okay, even if you go from this to this or this to this, it doesn't matter. The thing is, when you have to go from up to down, the contributions of going is coming from all the places where the quantum particle could have been at time Ti. You understand? That's the weird thing. So it is like uh, weird in terms of when you imagine in terms of particles, but when you imagine in terms of wave nature, in the wave nature, as I said, when you have this wave front and you want to calculate the intensity due to this wave front at a particular point P, then what happens? You calculate the sum of contribution of intensity from all these points, right? So somewhere you can see the wave nature is also entering the entire picture. When you try to think of this in a classical particle picture, it's not satisfying to look at that integration.
Yes,
Have
sir.
that integration in
Yes,
the
sir. But in your picture, you explain this wave nature. That's I understood. But this wave natures also originates from some source, right? But source must be localized within some region.
Can you give an example of what kind of source you're
Yeah,
talking
yeah.
about?
For examples, if we take let's say the experiment, single slit experiment, then also we have here a source, right? But source must be localized within some region, and from that
So
source,
you're talking about this single slit experiment,
yeah,
and there is some source here,
yeah,
and this source is emitting beams.
yeah, and then from this source, the beam which are emitting, they are spreading across the space.
Yes.
So they behaves like waves, as we know, right? So similarly in our case, that is that in that wave functions case also, first of all, I think that there must be some source which is present or which is localized at some initial positions,
Yeah,
and after that,
we can have those experimental conditions, but here we are looking at a very simple theoretical conditions. Think in this term that we have this wave function of a single particle at some point in space and time, and I want to find out what is the wave function of the particle at some other point in space and time. So I use the quantum tools and I do the calculations. Okay. And then I find out that when I want to find the probability or the amplitude at this position, I'm getting contributions at time Ti from various positions where the quantum particle could have been. I'm not saying it is there. I'm not even saying that the particle is there at multiple places at the same time. My particle is at somewhere near Qi at time Ti. But the particles could have been in different places in that time. And all these places where the quantum particle could have been, somehow they are also contributing to the evaluation of the final amplitude. This is what the integration inside it holds. That's the point. So we are looking at particle propagation, quantum particle propagation. Just maybe just you can think of one particle propagation. So I'm writing wave function of a single particle, right? So when I wrote psi of Qi Ti, I told you that I'm writing about a single quantum particle with this kind of wave function, and whose square is going to give you what is the probability of finding that single quantum particle at time Ti and position Qi, right?
yeah. But sir, here I have one more doubt. That here, let's say we took a single particles which is present at position QITH position. Okay, and from that QITH positions, these particles propagate from this position to our final position. then in that situations we can't have these the different positions for that
Again,
at
in that
initial
situation,
position. Yeah, in that case, I mean, in this case, we can't have this kind of diagram at initial positions that these particles can be present at this position. I mean, other positions
no,
like
that's
this.
what I'm saying. I didn't say the particle is present at different position,
Yeah,
but the contribution is coming from all other positions where the particle could have been. You understand?
yes, sir. But sir, I think it is the intermediate state between the initial positions and our final positions.
No. These are not intermediate state. We will come to that when we talk about Feynman path integral in few time, because in Feynman path integral, when we introduce these kind of things,
Yeah.
you will see the times are different. You will see that. I'll
Yes.
show you.
Yeah. Okay.
But here, the time is not different. You understand?
Yeah. At the same times, they can be present.
Yes. Because I think in Feynman path integral, you will see this is like
Yeah,
some
sir,
different
I think
times for different something like this. I don't remember, but we'll see.
yeah, but I think, sir, if this is the case, that is, if the same particles, suppose, can be present at some initial time at different positions, then it is purely
No,
relativistic
it is
quantum
actually not
particles.
present. Actually, it is actually not present. When I said we know the wave function,
Yeah.
that means I know that how it is localized somewhere near at this position.
Okay.
But
I mean, in that case, we don't have to worry about these other positions, right?
yeah, so it's like you cannot say, as I said, you always take the example of a wavefront of light and finding an intensity at point. At such cases, you don't ask where the light is, and if the light is here, then how can I take contribution from various places. So since the wave nature is entering the classical picture or the particle picture, that's why uh, there are some mathematics whose explanation can be weird.
Yeah.
Here we are getting a weird explanation. The integration is saying that, hey, look, we are getting contribution from all the places where the particle could have been, though my particle is at this position, right?
Yeah. But sir, actually, I confused with these explanations that we have here some wave, and then we want to find out these particles. But I want to know that from where these waves are actually came from. There must be some source, and that source must be localized, right?
At this point, we are not concerned about how the source has come, how the wave particle has come. We are not concerned. We are just talking about given you know. So as I started, given you know this
Okay.
from the very
Then
beginning,
it's fine.
given you know this. Okay.
Okay.
Given. So let me write it. So given you know this, is there a way in the quantum tool to know this? But because in the previous time, given you know this, you had Schrodinger equation to know this. But the whole idea was the only propagation or evolution in time could be known from the Schrodinger recipe. But we wanted a recipe, not just evolution in time, but evolution in both space and time. And that can only be given by a term called as propagator. And as we saw, how does the propagator look? It looks like this: QF and then e to the power minus I by h cross. Look, the Hamiltonian is coming here. So the Hamiltonian is going to decide what is going to be the propagator in this case. So if the Hamiltonian changes, then of course things can change, right? If it is a free particle, then propagator is going to be different. If it is a particle under some potential, the Hamiltonian is going to change. So of course the propagator is going to be different, and so on. So this is the new equation, you can say. It's not Schrodinger equation, but it's something new where given you know this, and then using this thing and the propagator, which is a function of QF, TF, QI, TI, you can know this QF, TF, right? So this is the whole idea that I wanted to convey. This is how the propagator, they enter the picture. The propagator only enters the picture when you talk about, you know, the wave function at a particular space and time, and you want to find the wave function at different space and time. That's when the propagator entered the entire picture. As we had Schrodinger equation, and Schrodinger equation only gave us evolution with respect to time, right? Using the time evolution of wave. So everything's clear? Okay. So we did this in the Schrodinger picture. Now, can I get the same form of propagator, which is this, when I do the whole thing in the Heisenberg picture? Of course, I should get, but it would be very interesting to see that, to see the whole calculation done in the Heisenberg picture. Okay. So this is where we end, and in the next part of the lecture, I'll continue with Heisenberg picture.